This video is on capacitors and capacitance. Question 1. What is a capacitor? What are its uses? Draw the symbol of a capacitor. A capacitor stores energy by electric fields, while a solenoid stores energy by magnetic fields. A capacitor is usually made up of two parallel plates separated by a distance little d. So this is the symbol of a capacitor. We got two parallel plates and there's a wire coming out of each parallel plate. So I'm going to go into detail later, hopefully, about this setup. We got a battery and a capacitor and a resistor all in parallel with each other. And we got these two switches. Question 2. What is the meaning of capacitance? Capacitance is a charge per unit voltage which can be stored in a capacitor. So C equals Q over V, which has units of coulombs per unit volts, which has units of farad. So Q is a magnitude of charge in one of the plates, and V is the potential difference across the plates. Remember, the units of V is joules over coulombs. So it's the amount of energy given to each amount of charge. Question 3. State the equation and define each variable which gives the capacitance of a parallel plate capacitor to its physical dimensions. So C equals epsilon A over D. Epsilon is the permittivity of the medium between the plates, has units of farads per meter. A is the area of one of the identical parallel plates, and D is the distance between the two identical parallel plates. So this equation tells you the capacitance in terms of the physical dimensions of the capacitor. So if there is a vacuum between the parallel plates, then E equals epsilon sub 0, or epsilon naught, which is 8.85 times 10 to the minus 12 coulombs over Newton meter squared. If we increase the area of the plates, then the capacitance increases. So A is in the numerator. If A gets bigger, capacitance gets bigger. And if we increase the distance between the plates, then the capacitance decreases, because D is in the denominator. Question 4. What is a dielectric? A dielectric, also known as an insulator, is a material between the capacitor plates which increases its capacitance. So E will always be greater than E sub 0. And if E is greater than E sub 0, take a look at this equation. If E is greater than E sub 0, then the capacitance increases, because E is in the numerator, eta. Capacitance is also in the numerator. If there is a dielectric, then the potential difference across the parallel plates V remains constant while Q increases. Okay. From this equation, C equals Q over V, so the capacitance will increase. Question 5. Draw 3 capacitors in parallel and state the equation when simplifying capacitors in parallel. So this is the setup we have, and using Kirchhoff's loop rule, we got V battery minus V capacitor 1 equals 0. Then V battery minus V capacitor 2 equals 0. Finally, V battery minus V capacitor 3 equals 0 volts. So V battery equals VC1 equals VC2 equals VC3. We'll just call it V sub C. This tells us that capacitors in parallel have the same potential difference. And they should have the same potential difference because they're all in parallel with each other. So Q equals, sigma Q, the total charge equals Q1 plus Q2 plus Q3. Q equals VC. So we have this equation here. We could factor out V sub C. So ta-da, we get this equation. If we want to simplify capacitors in parallel, it looks like the same equation as simplifying resistors in series. Question 6. Connecting capacitors in parallel leads to a larger capacitance. Question 7. Draw 3 capacitors in series and state the equation when simplifying capacitors in series. So, using Kirchhoff's loop rule, we have this. Plus V battery minus V capacitor 1 minus V capacitor 2 minus V capacitor 3 equals 0. We know Q equals VC. So solve for V. Q equals Q over C. So we're going to get Q1 over C1, Q2 over C2, Q3 over C3. Since these are capacitors in series, Q1 equals Q2 equals Q3 equals Q. So now we could simplify into this. So this equation for capacitors in series looks like simplifying resistors in parallel. Question 8. Connecting capacitors in series leads to a smaller capacitance. Question 9. Capacitors in parallel have the same potential difference or voltage, while capacitors in series have the same charge. Question 10. What are some equations for energy stored in a capacitor? Well, E is equal to 1/2 CV squared. And we could substitute Q equals VC. And solve for C, which is Q over V. So we get the second equation, 1/2 QV. And then we could substitute for V, which is Q over C, where we get the third equation. So we have 3 different equations for energy stored in a capacitor. Question 11. Draw a circuit which shows the capacitor charging. The circuit should contain a battery, resistor, capacitor, and wires. So this is the image we have. And now we're going to close switch 1. So when switch 1 closes, we have a current going through the left-hand side of the circuit. Current goes clockwise, the electrons go counterclockwise. Okay. So negative charge from the top plate moves counterclockwise and rests on the bottom plate. So what this means is the bottom part of the battery is going to have electrons moving counterclockwise. And electrons are going to build up on the bottom plates of the capacitor. So it becomes more and more difficult for electrons to move from the top plate to the bottom plate, since the bottom plate becomes more and more negatively charged. Okay, so if this top plate of the capacitor loses electrons, then it's going to become positively charged. If the bottom plate of the capacitor gains electrons, then this plate is going to be negatively charged. Okay. So eventually the electrons stop moving since the bottom plate is saturated with electrons, and the potential difference across the capacitor becomes equal to the battery. The current now goes to 0. Part B. Draw 3 graphs of voltage versus time, charge versus time, and current versus time when charging a capacitor. Label and give the equations of the graphs. So voltage versus time is going to look like this. Voltage is the dependent variable, time is the independent variable. So voltage is on the vertical, time is on the horizontal. And as time goes quickly, to a few seconds, the voltage across that capacitor is going to be the same voltage as the battery. Same thing with charge versus time. Current versus time, you see once the switch 1 is closed, the current through the circuit on the left side is going to be maximum, but within less than a second or two, less than a second, that current's going to go to zero. Part C, draw a circuit which shows a capacitor discharging. The circuit should contain a battery, resistor, capacitor, and wires. So we close switch 1 in part A to charge the capacitor. Now we will open switch 1 and close switch 2 to discharge the capacitor through the resistor. So what's going to happen now? The electrons on the bottom plate are going to move counterclockwise. So we want the negatively charged bottom plate to have zero charge, and the positively charged top plate to also have number of protons equal number of electrons to be zero charge. Okay. So the electrons on the bottom plate will move counterclockwise and the current will flow through the resistor. Part D, draw 3 graphs of voltage versus time, charge versus time, and current versus time when discharging a capacitor. Label and give the equations of the graphs. So voltage versus time is going to look like this. Okay. You could see RC is going to be equal to another variable called tau. Okay, it's a Greek letter tau. Charge versus time is going to look like this. And current versus time is going to look like this. You could see all 3 graphs look very similar to each other, right? It's going to be a constant times e to the minus t over tau. Okay. Question 12. What is the equation for the time constant? What are the units of the time constant? What does it tell us? The units is s, seconds, which is good because t over tau should have no units. Okay. Take a look at these following equations, okay? So after one time constant, the charge on the capacitor decreases to about 37% of its original fully charged value. This is one time constant. If T over RC is equal to 1. 2 time constants is if T over RC equals 2. Finally, 3 time constants is when T over RC equals 3. So after 3 time constants, the charge on the capacitor decreases to about 5% of its originally fully charged value. So question 13, we're given this following circuit, okay? We got the voltage of the battery, we got capacitor 1, 2, and 3. Let's solve for these unknowns, okay? First, let's solve for C equivalent. So we're going to use this equation to simplify the circuit to 1 battery and 1 capacitor. So we need to get a common denominator for these 3 fractions, and it's going to be 6. So I'm going to multiply each fraction by the number 1 so I could get a common denominator. So 11 over 6 farads is 1 over C equivalent. Take the inverse, which is 6 over 11 farads, to get C equivalent. So now we have 1 capacitor. We know Q equals VC. We were given V of the battery. So we solved for Q. Since these capacitors are in series, all the charges are the same. Okay? And now V1 is equal to Q1 over C1, V2 is equal to Q2 over C2, and V3 is Q3 over C3. So let's check if this is correct. V capacitor 1 plus V capacitor 2 plus V capacitor 3 is equal to 10 volts. So these should be plus signs here, okay? So I made a small mistake. These should be plus signs. Okay. Question 14, you are given the following circuit. We've got 3 capacitors in parallel. We got V battery, we know C1, C2, and C3. Let's solve for the following unknowns. So step 1, use this equation to simplify the circuit to 1 battery and 1 capacitor. So we get C equivalent as 6 farads. Now we have 1 capacitor, and the capacitance of this capacitor is 6 farads. We know Q equals VC, so it's going to be 60 coulombs. The total charge stored in all 3 capacitors is 60 coulombs. So we're going to use Kirchhoff's loop rule 3 times. We know V battery is equal to 10 volts. So VC1 equals VC2 equals VC3, it's 10 volts. And we know Q equals VC. So now this makes sense. Total charge is equal to charge C1 plus charge C2 plus charge C3, which is 60 coulombs. Question 15, we're given a circuit that has capacitors in parallel and series. Okay, we're given the voltage of the battery and we're given the capacitance of capacitor 1, 2, and 3. So let's solve for the following unknowns. First, let's simplify the circuit to have 1 battery and 1 capacitor. Okay, so first we simplify the 2 capacitors in series, which is 6 over 5 farads. Then we're going to simplify the 2 capacitors in parallel. Which is 11 over 5 farads. Now we have 1 capacitor. We know Q equals VC. And now we're going to use Kirchhoff's loop rule. Okay? So we know that the charge to capacitor 1 is 10 coulombs. And we know QC2 equals QC3 since both of these capacitors are in series. So we're going to use the loop rule again. And we get 12 coulombs. Now let's check if this is correct. We get 6 volts plus 4 volts is 10 volts. So everything is good. So you still need to remember Kirchhoff's loop rule. That's gold.